Hello everybody, in this lecture we will be solving 1994 IMO problem number 1. Here is a view of this problem. Let m and n be positive integers and let a sub 1, a sub 2 up to a sub n be distinct elements of the set 1 through n, such that whenever ai plus aj is less than or equal to n, we can find another element in the set such that this sum is equal to that element for some k. So we would like to show that the arithmetic mean of these numbers is no less than n plus 1 over 2. Let's start without loss of generality. We can assume that the AIs are ordered in increasing order and these are all less than or equal to n, because they are all taken from this set and greater than or equal to 1. So let's assume that the AIs are ordered in this way, and let I and j such that two indices such that this condition holds, AI plus a sub j is less than or equal to n. Then by the statement of the problem, this would imply that there exists a k such that ai plus aj is equal to ak for sure, but moreover what this tells us is that a sub I plus anything less than a sub j would also work. So a sub I plus a sub 1, a sub I plus a sub 2, all the way up to a sub I plus a sub j minus 1, all these terms are also somehow indexed within this set here. So therefore let's go ahead and index them. So let's make this equal to a sub k k sub 1. Let's call this a sub k sub 2, and so on. And let's call this one as a sub k sub j minus 1. And for the original one, a sub I plus a sub j, let's call this as a sub kj. So we have, if you will, this set of indices. So these indices k sub 1 all the way to k sub j happens to be a subset of the set. Obviously a sub k sub 1 is greater than a sub I itself, because a sub 1 itself is greater than or equal to 1. So therefore these are all a subset of I plus 1, I plus 2 up to m. The largest one can be a sub m if any, and so that's a subset of it. So therefore this would imply as a result that how many terms in this sequence? Obviously m minus I terms. So m minus I should be greater than its subset, right? So we are just counting in absolute values, and that would be greater than or equal to. So m minus I is greater than or equal to the count here, which is just j. So therefore whenever we have a sub I plus a sub j is less than or equal to n, then it implies that it implies this result, that I plus j is less than or equal to m. So therefore, alternatively, what I can say is if I replace this j with something slightly bigger, or you can say equivalently, so this implies that whenever j is less than or equal to m minus I, right? So if I replace this j with something slightly bigger, a sub, let's say m minus I plus 1, then this would make this whole thing greater than or equal to n plus 1, I should say, right? So this would have to be right because I just added something more than this constraint, right? So these indices add up to more than m, and as a result we will exceed this bound. But this would hold for I equals 1 all the way up to m. So finally, summing these inequalities across all the i's, we would get 2 times a1 plus up to a sub m is greater than or equal to, we have m terms here, m times n plus 1. And if you compare this expression with what was requested. So this would imply the arithmetic average here will be divided by m greater than or equal to n plus 1 all divided by 2, and that solves the problem. Hope you enjoyed the video and looking forward to see you guys in our next lecture.